Hello everyone. In this video, we're going to explore an essential concept in chemistry, dynamic equilibrium and reversible reactions. We'll discuss how a system reaches equilibrium and what happens to the concentration of reactants and products over time. So, let's start. So, first, what is a reversible reaction? So some reactions don't just go in one direction. They can go forward and they can go forward and backward. These are called reversible reactions and are represented by a double arrow, like the one you see over here. So, for example, A is in equilibrium with B and C. A reacts to give B and C. This means that while A reacts to form B and C, at the same time B and C can react to form A. This process continues until the system reaches equilibrium. Before I start explaining what is dynamic equilibrium, I'm just going to give you some examples of reversible reaction. And I want you to notice the difference between a forward and a backward, or what I call reverse reaction. So backward, or also called reverse reaction. So here, for example, the first equation, the forward equation would be N2 gas plus O2 gas to give 2NO nitrous oxide gas. That's the forward. Whereas if I am asked to write the reverse reaction or the backward reaction, I would say 2NO gas gives N2 gas, nitrogen and oxygen. That's the backward reaction. So another example. Again, let's write the forward reaction for this reversible equation. So the forward is H2 gas plus I2 gas, iodine gas, to form hydrogen iodide. That's the forward reaction. Now, the reverse, or what I call the backward, would be hydrogen iodide giving hydrogen gas and iodine gas. That's the backward. Sometimes there are questions in the tests and exams. They ask you to identify the reactants in a forward reaction, or identify the products. Similarly, identify reactants in a backward reaction and identify products in a backward reaction. So if I start in a forward reaction, H2 and I2 are called reactants, and HI is the product. Now, if I am dealing with the reverse or backward reaction, then HI now here is playing the role of a reactant, and H2 and I2 are playing the role of a product. Now, let's continue. What is dynamic equilibrium? When a reversible reaction occurs in a closed system, it will eventually reach a point where the rate of the forward reaction equals the rate of the reverse reaction. At this point, the reaction is in dynamic equilibrium. But why is it called dynamic? Because even though the concentrations of reactants and products remain constant, the reaction is still happening in both directions at the same rate. So first, let's give an example. So consider the reaction of nitrogen gas with hydrogen gas to produce ammonia, and I'm talking about a reversible reaction. So here we go. So at start, I only have reactants. I have N2 and I have H2 at start. I don't have product yet. So this is why the curve of NH3 is at 0, because no product yet is produced. So only reactants are present. So the forward reaction happens quickly. Now, as time proceeds, the concentration of hydrogen and of nitrogen decreases with time. And at the same time, the concentration of NH3 starts to increase. Now, as products form, the reverse reaction rate starts to increase. Meaning, at certain point, we can see clearly that I don't have anymore any change in the concentrations, meaning that H2 stopped decreasing, N2 concentration stopped decreasing, and the concentration of the product NH3 stopped increasing. What does that mean? Did the reaction stop? No, it did not. It means that this system reached equilibrium. At a certain point, NH3 started giving back N2 and H2 at the same rate, at the same speed at which N2 and H2 are giving NH3. So, and at this point, whenever we see the concentrations becomes constant, we know that our system reached equilibrium. So here, a chemical equilibrium, it's a state in which the forward and the reverse reactions, they balance each other because they take place at equal rates, at equal speeds. So the speed at which N2 and H2 reacts to give NH3 is equal to the speed at which NH3 reacts to give N2 and H2. So, law of chemical equilibrium states that at a given temperature, a chemical system may reach a state in which a particular ratio of reactant and product concentrations have a constant value. Now, in summary of what I said, 2 points you need to be aware of: that whenever a system is at equilibrium, the rate of the forward and the reverse. So look at this equation. The forward reaction rate slows down. The backward reaction, or the reverse, the rate of the reverse reaction increases until both of them becomes equal. When they are equal, it means system have reached equilibrium. At the same time, if we are discussing concentration and comparing concentrations, the the reactant concentration at a certain time will stop decreasing, and the product concentration at certain time will stop increasing, and both will have a constant, not equal, a constant reaction. So rate of forward reaction is equal to the rate of the reverse reaction, means we are at equilibrium, our system is at dynamic equilibrium, and concentrations of reactants and products become constant. Now, conditions of an equilibrium. How can a system reaches equilibrium? So at equilibrium, both reactions, they continue to occur. The system must be closed. Nothing added or removed. You cannot add more reactants or remove reactants. The forward reaction will equal in the speed the reverse reaction, and at that point, equilibrium is attained. Now, also in the dynamic equilibrium, we discuss equilibrium expressions. So, K equilibrium is called the constant, the equilibrium constant. And this expression can be written for any reversible reaction. So it's a numerical value. So let's say here's a reversible equation. K equilibrium will be, you take the products formula and you put each in brackets, because brackets means a concentration of C multiplied by the concentration of D. Now, sometimes in chemical equations, we have stoichiometric coefficients, we have numbers to balance. So this number will be written as a power. So concentration of C to the power of that number written next to it, multiplied by the concentration of D raised to the power of that number written next to it, divided by the concentration of reactants multiplied together. Now, of course, this K equilibrium is a numerical value. So if this K equilibrium value was a number more than 1, it means that in this reaction, or this reaction favors the products. So products are favored. Now, if this K equilibrium was less than 1, it means that this reaction favors the reactants. So you can imagine it like that. So it's giving, or it's more towards the, oh sorry, here I wrote B. So I meant to write C. So C plus D. Now let's take some examples and learn how to write the K expression of a homogeneous equilibrium. And I would like to explain to you what's a homogeneous equilibrium. If you look at all these reversible reactions, you will see that every reaction has the same physical state, like all of them are gas. So it's a homogeneous equilibrium. Now, I'm going to start writing the K equilibrium. You can pause the video, write the K expressions, the K equilibrium expressions, and then check your answers. So, let's start. That's question A. K equilibrium would be the concentration of the product. So I write NO2 in brackets. This 2, I write it to the power of 2, divided by the concentration of N2O4. That's it. Now let's take question B. So again, the K equilibrium will be the concentration of the products. Here we have 2 products. So it's going to be the concentration of S2 multiplied by the concentration of H2. Now S2 I only have 1, so it's just 1, or raised to the power of 1, and H2 is raised to the power of 2 divided by the concentration of H2S. Here's the reactant full formula, H2S to the power of 2. Let's take another example. Working out to solve question C. K equilibrium is equal to the product. Here I have 2 products, so it is CH4 multiplied by H2O concentration. Remember to put these formulas in brackets, divided by the concentration of the reactants, and I have here two reactants, so it is H2 raised to the power of that number multiplied by CO. Another, let's do D. So here we have K equilibrium is equal to the products. I have two products, H2O in brackets multiplied by NO in brackets. Now H2O, there's a number next to it, so it's raised to the power of 6, and 4NO means raised to the power of 4 over concentration of NH3 to the power of 4 multiplied by the concentration of O2 to the power of 5. Finally, the last practice, K equilibrium will be equal to H2, the product, multiplied by CS2 concentration, H2 hydrogen gas, raised to the power of 4 multiplied by the concentration of CS2 divided by the concentration of the reactants. Here I have two reactants, H2S raised to the power of 2 multiplied by concentration of CH4. That's it. So this is an example of writing the equilibrium constant expressions for homogeneous equilibrium. Now, what if I have a heterogeneous equilibrium? And what do I mean by a heterogeneous? If you notice here, the reactant and product, they don't have the same physical state. So one is gas, one is solid, not the same. One is gas, one is liquid. Solid and gas. Solid, while the others are gas. Solid, gas, solid, and gas. So here, I don't have the same physical state in every system at equilibrium. So I call this system heterogeneous equilibrium. Now, why it is important, or what does it change in writing the K equilibrium for heterogeneous equilibrium? Actually, in a heterogeneous equilibrium, you do not involve any reactant or product that is in the solid or in the liquid state. These will not be involved when writing the formula of K equilibrium. So I'm going to start with the first example. So since this is solid, I will not include it in the formula. So I'm just going to say C10H8 concentration, and that's all. So you can put over 1, or you can just say that's it. Now B, K equilibrium is equal to only H2O gas. I'm not going to include the H2O liquid. For part C, these two will not be involved in the formula. So K equilibrium will be only the concentration of CO2. One more example, two more examples. D, this will not be involved because it is solid. So K equilibrium is equal to hydrogen gas concentration in brackets multiplied by concentration of CO divided by the concentration of water gas. And last example, K equilibrium is equal to Fe and FeO will not be involved in this formula, in this equation. So it's the concentration of CO2 over the concentration of CO. Now, moving on. In the K expression, sometimes you might read in the question Kc or Kp. Now, K, both of them are K equilibrium. So if I just want to be more specific, I can say write Kc, and C stands for concentrations. What we were writing over here. A concentration is symbolized by the brackets, and you write the formula inside. Whereas when they say Kp, it means the equilibrium. The question is asking you to write the equilibrium constant expression for pressure. P stands for pressure. So at this point, you cannot put the formula in brackets. You will have to write pressure of that formula. Let me give you these 3 examples. So here they are asking each part to write the Kc and the Kp. So Kc, or K equilibrium, it is equal. I'm talking about A. Liquid will not be included in the formula of K equilibrium. So it's going to be NH3 product raised to the power of 2 divided by hydrogen gas raised to the power of 7 multiplied by nitrogen dioxide raised to the power of 2. If I am writing a P expression, the K equilibrium of pressure, in this case, I would use P instead of brackets. So it's going to be the pressure of NH3 squared, the pressure of hydrogen gas to the power of 7, and the pressure of NO2 squared. You need to write that big letter P. You need to write P. P represents pressure. It's the symbol of pressure, whereas brackets is the symbol of concentration. Now let's take another example. Part B, equation B. Again, before I start writing Kc equilibrium constant, the solid reactant and product will not be involved. So it is only the concentration of SO2 raised to the power of 2 divided by the concentration of O2 to the power of 3. And if I am writing the equilibrium constant expression of the pressure, that would be pressure of SO2 squared divided by pressure of O2 cube. So again, you're writing P, not brackets. Now the last example, Kc. This will not be included in the formula of Kc because it is solid. So it is the concentration of CO squared divided by the concentration of CO2. And here, K, pressure, or the constant expression, the equilibrium constant expression for pressure would be pressure of CO squared over pressure of CO2. And that's it. Thank you for listening.